Okay, so good afternoon, everyone. So my name is Juan Sebastián Empaque, and I'm going to talk about tensor products of quiver bundles. So a motivation to study quiver bundles for me comes from my study of Higgs bundles, and in particular, instances of quiver bundles arise as fixed points for the natural C-star action on the moduli space of Higgs bundles over a compact Riemann surface. For this particular project, the motivation comes from an article of my advisor, Peter Goten, and a former student of his, Azucena Sad, in which they introduced a quiver bundle whose polystability has important consequences in the deformation theory of moduli spaces of holomorphic chains, which are those quiver bundles that appear as fixed points for the C-star action that I was just talking about. So the task that my advisor gave me was to find a representation theoretic interpretation
Sorry, guys.
of quiver bundle. I'm sorry? Everything okay?
Still very faintly. I'm sorry.
Okay. So, okay, so somebody of me is saying that the sound is very low. You see? So maybe I should switch to my iPad.
Okay, so can you hear me better now?
Yes, yes, much better.
Yes.
Okay, so
Okay, so I was saying that for this particular project,
okay, so sorry, I was having issues with my connection in the iPad, but okay. So I was saying that the motivation for this particular project comes from a work of my advisor, Peter Goten and Azucena Sad, in which they introduced a quiver bundle whose polystability has important consequences in the deformation theory of moduli spaces of holomorphic chains, which are those quiver bundles that appear as fixed points for the C-star action on the moduli space of Higgs bundles. So the task that my advisor gave me was to find a representation theoretic interpretation of this quiver bundle. And it turns out that this is an instance of the tensor product of representations that I study in my work. So this is today's agenda. So first I will give some basic definitions and results. Then I will define what a tensor product of representations is. And finally, if time permits, I will show some applications. Okay, so let's start. So I will fix a quiver Q, a ring space XOX, and a family of modules M indexed by the edges of the quiver. So a twisted representation of Q is given by assigning to each vertex of the quiver an OX module, and to each edge of the quiver a morphism between the previously assigned OX modules twisted by the twisting module corresponding to the edge M alpha. So a morphism of twisted representations is given by a family of morphisms of OX modules indexed by the vertices of the quiver, for which the obvious diagram must commute. Okay, so the category of twisted representations of the quiver Q is abelian, meaning that we can use all the tools from coming from homological algebra to study these representations. So if you don't want to work in the general setting of ring spaces, you can choose to work with the full subcategories of representations in the categories of coherent sheaves over a Keller manifold, or you can study representations of quivers in the category of quasi-coherent sheaves over an scheme. Okay, so a very simple example of twisted representation of a quiver is that given by Higgs bundle. So let me recall that a Higgs bundle over a curve X is a pair E phi, where E is a holomorphic vector bundle over the curve, and phi is an endomorphism of the vector bundle E twisted by the canonical bundle of the curve. So one can think of such an object as a representation for the Jordan quiver, for which the twisting morphism is the dual of the canonical bundle. Okay? Okay, so in representation theory of quivers, it is often more useful to study instead modules over the path algebra of the quiver. Okay, so let me explain what I mean by this. So given a non-trivial path of the quiver, we define the twisting module MP to be given by the tensor product of all the twisting modules associated to all those edges appearing in the path. If the path that I'm taking in the quiver is the trivial path, then I set MP to be the trivial path OX, the trivial module OX. So the twisted path algebra of the quiver Q is the sheaf of OX algebras whose underlying OX module is given by the direct sum running over all paths of the quiver of these twisting modules MP that I have just defined. And the product rule in this algebra is given as follows. So if we take two sections, MP and MQ, in the corresponding twisting modules MP and MQ, then their product is going to be equal to the tensor product of sections if the head of the path Q equals the tail of the path P, and zero otherwise. Okay? So I define a module over the path algebra as an OX module M, and sorry for the redundancy, which has a compatible structure of module over the twisted path algebra. So this is the same as saying that we have an OX linear map mu that goes from the tensor product of the twisted path algebra with M into M, for which the usual axioms of modules over algebras hold. So we say that amorphism we define amorphism between modules over the twisted path algebra as an OX linear map which is compatible with the structure morphisms mu. This compatibility condition is expressed by asking the diagram that you can see here in the slides to commute. So a result of Bartocci, Bruzzo, and Rava that generalizes the well-known results for classical quiver representations tells us that the category of twisted representations of the quiver, the category of modules over the twisted path algebra of the quivers is isomorphic to the category of twisted representations of the quiver Q. Another key ingredient in our definition of tensor products is that of representations with relations. So a relation on the quiver Q is a formal sum running over all paths of length greater than 2 with a fixed tail and a fixed head of terms of the form Cp times P, where Cp is a global section of the structure sheaf OX. Okay, so now if we take any set of relations of the quiver, I can produce a double-sided ideal of the twisted path algebra by taking as generators a subset of these sets Ru, which I construct from the relation as follows. So for each relation in the set of relations R, I replace each path by a local section MP in the corresponding twisting module. Okay, now an observation is that because of the equivalence of categories that we have before, tensorization by the map, by the local section MP gives me a morphism between the modules, OX modules, assigned in the tail and the head of the path. So I define a twisted representation with relations as a representation for which every generator, for which the morphism induced by every generator of the ideal is 0. So now I have the following generalization of our previous equivalence of categories. So the category of twisted representations with relations of the quiver Q is equivalent to the category of left modules over the quotient of the path algebra modulo the ideal of relations. And this equivalence of categories is compatible with the one that I have before, in the sense that the diagram that you see here in the slides, the diagram of functors, this diagram of functors is commutative. Okay, so we are now more close to define what tensor products of representations are. So first, before doing so, one more definition. So given two quivers, Q prime and Q double prime, we define the tensor product quiver to be given by the following data. So the set of vertices of the first quiver times the set of vertices of the second quiver. And set of edges of this quiver will be set of edges of the first one, set of vertices of the first one times set of edges of the second one, union with set of edges of the first one times the set of vertices of the second quiver. Okay, so for instance, if alpha is an edge of the first quiver and j is a vertex of the second quiver, the head of this edge will be the vertex given by head of alpha comma j. So perhaps this notion of tensor product quiver is better seen through an example. So here in the slides, you can see what the tensor product of two type A2 quivers looks like. Okay, so now the last ingredient before defining quiver representations is the following. So we have an isomorphism between the tensor products of the twisted path algebras of the quivers Q prime and Q double prime with the twisted path algebra of the tensor product quiver modulo some ideal of relations. So let me explain what is the twisting that I am using here on the left-hand side and what is the ideal of relations. So here, for an edge of the form alpha j, where alpha is an edge of the first quiver and j is a vertex of the second quiver, the twisting module will be defined as the twisting module m prime alpha. And similarly for all those edges of the form I beta. And now the ideal of relations is defined as you can see here in the slides. I will not explain it, but what you have to keep in mind is that with these relations, what we are trying to say basically is the following, that if in the tensor product quiver, you follow the path T of alpha beta, alpha head of beta, this is the same as following the path alpha T of beta, head of alpha beta. Okay, so I am now ready to define what tensor products of representations are. So if I take two twisted representations of the quivers Q prime and Q double prime, by our first equivalence of categories, I can assign to each one of these representations modules over the corresponding twisted path algebras. Now, the tensor product of these modules has canonically a structure of module over the corresponding tensor of the twisted path algebras. Now, because our previous proposition, this is the same as having a module over the quotient of the twisted path algebra of the tensor product quiver modulo some ideal of relations. And because our second equivalence of categories, this is the same as having a representation of the tensor product quiver with some relations that I can read from the data of the ideal of relations I. Okay? And this representation that I obtain is what I call the tensor product representation. Okay, so let me show what happens when the twisting is trivial. So if we tensor two representations, as our theorem says, I obtain a representation of the tensor product quiver, right? And this representation locally looks as you can see here in the slide. So for instance, to the vertex T of alpha, T of beta of the tensor product quiver, I will assign the tensor product of E prime T alpha and E double prime T beta. And for instance, to the edge alpha T of beta of the tensor product quiver, the morphism that I will assign will be given by the tensor of phi of alpha with the identity on the second component. In particular, if we restrict ourselves to classical quiver representations, we recover the notion of tensor product that has been studied by Herschen and Das and collaborators. Okay, so now I will go into some applications. So from now on, I will restrict for simplicity to untwisted representations, and I will consider either quiver bundles, which are representations of quivers in the category of holomorphic vector bundles over a compact Riemann surface, or classical quiver representations, which are obtained by assigning to each vertex of the quiver a finite dimensional vector, complex vector space. So if I take a representation and an stability parameter with real entries indexed by the vertices of the quiver, I define the theta slope to be given by this quotient that you see here in the slides. So this slope is an hybrid between the usually Mumford stability condition for vector bundles and the stability condition for quivers given by King. Okay, and with respect to this theta slope, I have notions of theta semi-stability and theta polystability with respect to sub-objects. Now, the following result relates polystable representations to some solutions of a partial differential equation. And this result is known as the Hitchin-Kobayashi correspondence for quiver bundles and is due to Alvarez Consul and Garcia Prada. So the result tells us that a quiver bundle is theta polystable if there exists an Hermitian metric on each one of the vector bundles that I assign at each one of the vertices of the quiver, for which the following gauge-theoretic equation holds. And why do we care about this Hitchin-Kobayashi correspondence? Well, I used this correspondence to show that tensor products of polystable quiver bundles is polystable for an stability parameter that will depend in those stability parameters of the corresponding representations that I am tensoring. So at this point, like several questions arise. For instance, does every polystable representation of the tensor product quiver comes from tensor products of polystable representations? And what sort of analytic or algebraic structure does the set of decomposable representations have? So recall that for vector spaces, we know the answer. This is the Segre embedding. And we were able to give an answer to this question in the quiver situation for classical quiver representations. So let us consider the moduli space of theta semi-stable quiver representations of a fixed dimension T. So we can construct these moduli spaces from using two different techniques, one using Mumford's GIT and the other using symplectic reduction. Uh, Both methods yield the same moduli space, and the points of this moduli space classify as equivalence classes of semi-stable representations or equivalently polystable representations up to isomorphism. And our result is as follows. So we pick two acyclic quivers and we pick generic dimension vectors and stability parameters. So by this genericity condition, I mean it's a technical condition that basically says that the moduli spaces that I will obtain from symplectic reduction will be manifolds. So the tensorization map of representations, which is well defined by the previous theorem, descends to the moduli spaces. And this map will be an embedding whose image is a submanifold of real dimension that depends on the Euler forms of the quivers Q prime and Q double prime. Finally, I would like to discuss a connection between the tensor products that I have been studying with character varieties. So the first lemma says the following, is that a tensorization of representations induces a map between the moduli space of n-dimensional representations of the Jordan quiver and the m-dimensional representations of the Jordan quiver into the moduli space of commuting matrices modulo the action by conjugation by GLD. Now, let me recall that the GLN character variety of the group CR is the GIT quotient given by the representation variety modulo the action of the general linear group. So now I can see that the rank 1 character variety is an open affine subset of the moduli space of n-dimensional representations of the Jordan quiver. And the same for the character variety, the rank 2 character variety inside the moduli space of commuting matrices modulo the conjugation action of the general linear group. And moreover, one can see that the tensorization map restricts to these open subsets. So now my task is to study the scheme theoretic image of this morphism. So the scheme theoretic image will be the affine scheme of the rank 2 character variety determined by the kernel of the ring map associated to this tensorization morphism. As a topological space, the scheme theoretic will be the scheme theoretic image will be the closure of the set theoretic one. So in this way, we recover an irreducible closed subscheme of the rank 2 character variety. And following the stream of ideas from my talk, I call this the Segre subscheme of the character variety. Now I can play the same game and recover Segre subschemes for higher rank character varieties by considering tensor products of arbitrary number representations of the Jordan quiver. So that would be all. Thank you very much. Is there any question?
Thank you.
Juan Sebastian, are there questions or comments?
May I ask a question?
Yes, go ahead.
Have you, Juan Sebastian, have you considered any sort of instability for this tensor product of quivers? Understanding hardness and filtrations or unstable points in the category of all tensor products of quivers?
No, I haven't, but I think it's a really interesting idea to pursue. Yeah.
Because so far the stability result is the polystability correspondence between two
Yeah, right.
representations and the
So-
tensor product, right?
Yes. So yeah, actually, I think it's kind of a work in progress with my advisor to work the semi-stability in using just not using the Hitchin-Kobayashi correspondence, but using just algebraic methods. And there is like a work by Balaji and Parameswaran in which they do this for the case of Higgs bundles, and they say that their method could be adapted to the quiver bundle situation. And their idea is basically to translate the problem into the principal bundle setting and to study stability of sections in the sense of Bogomolov. So yeah, this is kind of the idea. Yes, but it's still pending. Yeah.
Okay, thank you.
Are there more questions or comments for Juan Sebastian?
Can I ask something too?
Yes.
Marcos, please.
Yeah, so I think the Álvarez Consul Garcia Prada result that you mentioned is for the untwisted representations, right?
No. It's actually for twisted
It's for twisted.
representations, and
Okay.
actually it works for arbitrary for an arbitrary Keller manifold, projective Keller manifold. Yeah.
And twisted representations of the quiver, you have that vortex type equation. Yeah.
Yes. These are the quiver vortex equations, actually. Yeah.
Uh-huh.
Which in some sense is an moment map condition, right? Because it's both the moment map of Attila bot and the moment map coming from a king of on the quiver side. So yes.
Sure, thank you.
Any other question or comment? Thank you.
Thank you.
Marcos, are you ready? Good.
Can you see my screen now?
Yes, we can see your slides right now. Great. Okay. Our next and last speaker
due to last time cancellation from our colleague Jesus. Our last but no less important speaker will be Marcos Jardim to close our character varieties and Higgs bundle session. He is from Universidade de Campinas, no Brazil, and he will talk about coherent systems on integral curves. Thank you very much for being here, Marco.
Thank you, Ronald, for the presentation and for inviting me to participate. I'm sorry I couldn't stay there. I couldn't be there this time. But thanks everyone for attending this this talk. So I'm going to talk about the first part of some work that we just finished with Leonardo Roa Leguizamon and Renato Vidal Martins here in Campinas. Here's the outline of my presentation. So I'll start in these first two sections, giving some definitions and presenting some key elements. The main results of today are in these parts 3 and 4. And finally, I'll very briefly talk about our main motivation and application for the bounds that we find, which is the construction of bridge-loan stability conditions on the category of on the derived category of coherent systems on an integral curve. So today I'll take C to be an integral curve, possibly singular, right, of arithmetic genus G. So G will be the arithmetic genus. Remember that a coherent system on a curve consists of a triple. It's a coherent sheaf of rank n and degree d, and a k-dimensional vector space, V, together with a linear map from the vector space to the space of sections, to the space of global sections of the sheaf. And a few definitions, we say that the system is injective if this morphism phi is injective, and hence the notation, we simplify the notation by simply omitting the map phi, thinking of V as a subspace of the space of sections. This is pure if E is a torsion-free sheaf and phi is injective. And finally, we say that the system is complete if phi is an isomorphism, right? So V is just the space of the whole space of sections, right? So in the work we do, it turns out to be important to consider some weird coherent systems like the structure sheaf of a point and the zero vector space, right? So we can take E to be the structure sheaf of a point, V to be the zero vector space, or even we can also take the zero sheaf and some vector space V, and also again phi would be the zero map, right? So in order for us to say that the category of coherent systems is abelian, to work on an abelian category of coherent systems, we have to include these type of objects. Otherwise, sometimes you may not have co-kernels, especially. And this type of objects have been around for a long time, at least 30-something years. They were first introduced by Newstead, Lepotier, and perhaps a few others. But first they appear as a generalization of linear systems, which is the case when the rank is 1. So linear systems mean n equals 1 when the coherent sheaf is just a line bundle or a rank 1 torsion-free sheaf. Also, it's interesting from the point of view of Brill-Nether theory. So these are the main motivations to study these objects. Remember the stability for sheaves. So this has been spoken about here in this meeting today. So coherent sheaf, always on a curve, is going to be stable if every proper non-trivial subsheaf admits has a slope which is smaller than the ambient sheaf, right? So the slope of the sheaf is just this quotient of degree divided by rank, or it's a plus infinity when rank is said to be plus infinity when rank of E is 0, when E is a torsion sheaf. And then a sheaf is semi-stable if this inequality is satisfied for every proper non-trivial subsheaf. And remember that sheaves always admit Harder-Narasimhan filtrations. So you have a filtration of E by subsheaves, EK up to E1, with this property that the quotients are always slope semi-stable, and the slopes of these quotients are decreasing in the following sense. So the G1 has the maximal slope, which we're gonna denote by mu max, and the GK has the smallest slope, which we are gonna denote by mu min. So please stop me if you have any questions. And similarly for systems, now we have a notion of alpha slope, slopes depending on a real parameter, positive real parameter, that is defined like this. So the alpha slope of a triple will be just the degree plus this parameter alpha times the dimension of V divided by the rank. Okay. And the system is said to be alpha stable if every proper non-trivial subsystem always has smaller or smaller than equal in case of semi-stability, smaller than or equal of this alpha slope. So just to make it clear what I mean by a subsystem, it's just some subsheaf E, such that when you look at the commutative diagram, okay, so this map, let's give it a name to this map. I don't know. This map alpha, no, alpha is not good. This map, I don't know, eta, induces a morphism from H0 of F to H0 of E. Now we also have these maps W to sections of F and V to sections of E. And then we need another linear map here, T, such that this diagram commute, right? So a morphism in this category is this pair of an eta going from F to E, and the linear map T going from W to V, right? Such that this diagram commutes. So this is the notion of a morphism in this category of coherent systems, and that's what I mean by a subsystem, right? So it's a subsystem when both eta and T are injective maps. And with these definitions, Harder-Narasimhan filtrations also exist in this category of coherent systems with this notion of alpha stability. Now, let's go for the results that we are including the first part of this paper with Leonardo and Renato. So if E is a coherent sheaf on the curve C, on the integral curve C of rank n and degree D, then if the maximum slope is negative, then there are no sections. And if the minimum slope is non-negative, then the number of sections is always bounded by D plus N. Right? Moreover, this bound is sharp, right? So a semi-stable sheaf satisfies the equality if and only if either it's a torsion sheaf, right? So when it's a torsion sheaf, the H0 of E is just the length, right? So counting the points with a multiplicity, and this is equal to the degree of the torsion sheaf. When you have a rational curve, this is always the case, right? Because when you have a rational curve, we know that E is a sum of all AIs like this to n the rank. Mu min positive means that all the AIs are non-negative. And then we know that H0 of E is equal to the sum of these, AIs plus 1, which precisely give us D plus N. Okay. So this is the case of rational curves that the bound is satisfied. And also for trivial bundles on any curve, because then degree is 0 and the number of sections is equal to n. So these are the only situations when the bound is attained on the integral curve. This result was known even by Lepotier in the 90s for smooth curves and semi-stable sheaves. So instead of these conditions on the mu max and the mu min of the sheaf, Lepotier puts the condition that the sheaf is semi-stable, then H0 is smaller or equal than D plus N. Any questions? So here, I guess it might be interesting to understand when H0 of E is 1 less than maximum. It's D plus N minus 1. Right? So for each sheaves, this equality holds, and so on. So try to characterize these other equalities. So this is a curiosity. Now, there is also the so-called Clifford's theorem for sheaves. So if E is a coherent sheaf with such that the mu max and mu min are in this interval between 0 and 2G minus 2, then we always have this other bound, this better bound on the number of sections. Right? And note that when the slope of E is larger than 2G plus 2, so so when the slope of E is larger than this bound here, then Riemann-Roch theorem tells us what is the dimension of H. Right, so tell us what is the dimension of the number of sections, because semi-stability implies essentially that H1 of the sheaf vanishes, so H0 is just given by Riemann-Roch, and that's the dimension of H0 given by Riemann-Roch. And again, this result was known by it's in a paper by Brambilla Paz and these other two authors and her co-authors, again, for smooth curves and semi-stable sheaves. So we are replacing smoothness by integrability and semi-stability by this other condition here on the slopes. Now, for coherent systems, we have a similar bounds. Now, instead of being on the number of sections, we get on the K, which is the dimension of the vector space in the system. Note that, as I mentioned before, mu stability, alpha stability or alpha semi-stability implies pureness. And here, I think we can remove pureness as well, because mu stability implies pureness, and then we already know that by this condition that it's pure, it means that K has to be smaller or equal than H0 of E, right? So if the sheaf E, if the sheaf in the system already satisfies the condition of the first result, then this bound here is obviously attained, right? So this bound is just a consequence of the previous result. The remark here is that the hypothesis is different, is that mu alpha min of the system. So now you look at the Hadamard-Azimuth filtration of the system. And if this mu alpha min is non-negative, we again have this bound for K. And if the slopes, the alpha slopes for E, right, the mu alpha min and mu alpha max are in this interval between 0 and 2G, then we get something similar to the Clifford's theorem as well, right? So this is now a generalization of result by Lang and Newstead. Again, that was known to be true for smooth curves and semi-stable systems, alpha semi-stable systems. And the observation is again that this first bound here is sharp, and we can characterize what are the systems that satisfy the bound. One is the trivial complete systems. So remember, this notation here means that that the sheaf is trivial, and what else? The vector space is just isomorphic to H0 of OC n. So only these complete trivial systems satisfy the equality when the genus is at least 1. And these are the systems that satisfy the equality when G is equal to 0. These are this sum of complete systems. So these are the results that I wanted to present, which are small generalizations of results known in the literature for smooth curves and semi-stable systems. And the main motivation behind these results, how do we find them, is because we were attempting to construct stability conditions on the derived category of coherent systems on an integral curve. I'm not going to go too much into stability conditions on derived categories because that would take more time than we have today. But in a nutshell, in just 2 minutes, what we do is we consider these tilting categories, right? So we take parameters alpha and beta, non-negative, and define these full subcategories of the category of coherent systems. So this is the abelian category of coherent systems on C. Then this full subcategory of the T here, this curly T, is all those systems E, such that every quotient system always has alpha slope larger than beta. And the other free part of the category consists of all the systems such that every subsystem always has alpha slope smaller than this given number beta. Okay. This is what is called a torsion pair in the abelian category of coherent systems. So this is a torsion pair. And given a torsion pair, you can perform this construction known as tilting and define a new abelian category, which are denoting by this co-cis alpha beta. So this is a new abelian category that is a heart in the derived category of coherent systems. Okay. Never mind too much what is a heart. But a stability condition consists of these two elements. One is a heart in the triangulated category, the heart in the derived category of coherent systems, plus a stability function. A stability function is a group homomorphism from the Grothendieck group of the abelian category into the complex numbers. And with this precise formula here, we can show that this is a stability function, which means that whenever the imaginary part vanishes, the real part has to be negative, right? And this is what, maybe there's a minus sign. Yeah, I guess I missed a minus sign here because what is in parentheses is positive. So there should be a minus sign here. And that's where this inequality comes in, right? Because d plus n minus k is always non-negative. And if we add a positive multiple of n is always positive. So if we add a positive multiple of n, right? Not a positive multiple, but something that is larger than n, then this quantity here will be always negative for whatever whenever you have a system that for which this quantity here is zero. Right? So this is what we wanted to prove, and it was in the attempt of proving this sign condition for the real part of this stability function that we found those inequalities, and that's where why they are important in this context. So thank you very much, everyone. That's all that I had for today. Thanks for the attention, and thank you.
Great, Marcos. Thank you. Are there questions for Leonard Nimoy? Sorry, for Marcos. Are there questions?
Sorry, Ronald, I can barely hear you.
May I ask something?
Yes, absolutely.
Do you have any idea about the wall crossing problem for these stability conditions you obtain for different parameters?
Yeah, we in our paper we worked out some walls, right? So we know that when the parameters are sufficiently large, then a system is going to be Bridgeland stable if and only if it's alpha stable. Okay?
Mm-hmm.
But we haven't really understood the intermediate walls, right? So we also have a vanishing wall. We know that for some systems we have a wall below which there are no Bridgeland stable systems, right? But we haven't. It's quite hard, right? So to really so far, right? So we found it quite hard to get a grip on characterizing the walls and understanding the wall crossings. But thank you for your question. That's
yeah, thank you.
Very good question. Thank you.
It's a tricky question. Yeah.
Are there more questions or comments for Marcos? Actually, maybe I have a couple of silly questions, Marcos. I guess there is a possibility to get a SHATS certification from the Gardner-Simon filtration of those alpha slopes. Is it possible and would be useful for something?
Can you repeat the question? So it's a stratification?
Yeah. From this Gardner-Simon filtration, is it possible to get a, well, I guess there is a moduli space of coherent systems, right?
Yes.
And if so, then is there a possibility to get a SHATS certification from this Gardner-Simon filtration?
Yeah, you mean understanding moduli spaces for systems that are not stable with a fixed Gardner-Simon filtration. I guess that's possible, right? So this has been done by for curves alone. I think results by Vicky Hoskins and maybe others. This is the problem that they work on, right? So understanding moduli space of sheaves that are not stable, but with a fixed Gardner-Simon filtration. I guess that would be possible as well. And I think these problems that people were speaking earlier on about the Segre invariant, and that's probably viable also for systems, understanding Segre invariant and for systems as well.
Okay, thank you. If there are no more questions, let's thank again to Marcos. Very nice, interesting talk.
Thank you very much, Ronald.
And thank you all for joining us to this character varieties and Higgs bundle session. This was very, very useful and very enlightening for us. I hope you really enjoy it. Tomorrow we will have more thematic sessions. No, tomorrow no. On Friday. On Friday there will be more thematic sessions. I'm not sure if they will be available online. They will be just okay. Just one. Okay, the plenary talks will be available online. So this is it for today, and thank you very much once again. Bye-bye.
Bye, Ronald. Thank you very much. Bye, everyone.
Bye, everyone. Thanks a lot. Have a good day there.
Thanks.
Thank you.